Hello students, I am Dr. Tanmoy Vishwas. I welcome you all in my channel Chemistry, the Mystery of Molecules. I hope you all are fine during this tough time. So let's discuss today about an interesting topic, that is aromatic electrophilic substitution or AES reaction on pyridine, which is a six-member heterocyclic compound. By the way, pyridine by nature is electron deficient and deactivated substrate. So today we will learn how to functionalize this deactivated substrate with different electrophile and get the selectivity of the product, actually mainly the meta product. So today's discussion will cover the points like is pyridine activated or deactivated and why, and this should be explained based on the resonance structure, and finally we'll discuss its reactivity with complete mechanism, and finally some examples where the low reactivity is observed and how to overcome this difficulty with some modification. So a lot of chemistry to be learned in this video. I request you please watch this video in a cool mind and watch the video completely such that you can enjoy the flow of chemistry completely. Okay, let's start. So first discuss about the electronic distribution pattern. By the way, remember that pyridine, this is actually a aromatic molecule. Okay, it has aromaticity, but interestingly the lone pair of this orbital which nitrogen possesses is in the sp2 orbital, and actually it is not involved in the aromaticity. Please keep this thing in mind. But there is another electron, single electron in the p orbital, which is involved in the aromaticity of the pyridine. By the way, we know that nitrogen is actually electronegative heteroatom. So if it is electronegative, it will prefer to hold or drag the bond pair or the electron cloud of the aromatic nucleus towards itself. Okay, this is the actual definition, and by resonance, if we want to express this, we can express in this way. How? See, this pair of electron can come to the nitrogen. Consequently, the carbon ring will have a positive charge and nitrogen will have the negative charge. And this negative charge is somehow stabilized due to the higher electronegativity of this nitrogen atom. By the way, similar phenomena is observed in case of nitrobenzene. Okay, the similar resonance structure is possible because this bond can come here, it can come. So always remember the central nitrogen will bear the positive charge. Okay, so what happens? Positive charge created at this center and the negative charge generated on this oxygen. Fine. So we know that this nitrobenzene is a deactivated substrate for Fc alkylation or Fc reaction, Friedel-Crafts reaction, and that's why this nitrobenzene is used as a solvent. So similar type of property we may expect from pyridine because of this, because of its withdrawing nature. So it's a deactivated substrate. And if we draw further canonical form, for example, if the pair comes here, so positive charge will go there. By the way, negative charge should be here. Okay, similarly another canonical form, this. So what is the conclusion? First of all, pyridine is deactivated for aromatic electrophilic substitution because of the heteroatom present in this nucleus. Fine, point number one. Second, there is an additional disadvantage or deactivation procedure. How? For example, this nitrogen has a lone pair, and we know that nitrogen is actually a hard center. So this is actually a hard center. So it will prefer, actually this is a basic in nature and hard center. So what can happen? It can react with proton H plus to be protonated, or it can react with a Lewis acid which has vacant orbital, and in that vacant orbital the lone pair of nitrogen could be delocalized and both will be stabilized. Mean this pyridine as a Lewis base and the Lewis acid adapt. So this way the activity further reduces. First of all the electronegativity, second of all the basicity or adapt formation. So that's why pyridine shows very less reactivity in Friedel-Crafts reaction, or better to say any type of aromatic electrophilic substitution. So it's a low reactive substance. Okay, so let's discuss how much low the reactivity actually is. Okay, by the way, to understand that, we need to discuss the reactivity of pyridine with a electrophile, because we are discussing its reactivity for aromatic electrophilic substitution, and we will understand why the meta substitution for pyridine is favored over ortho and para. Okay. So in order to understand that, let's first name this nucleus. For example, this is alpha, this is beta, this is gamma. Similarly, this is also beta, this is also alpha. Okay, so now you may consider alpha as a ortho, or you may consider that beta as a meta and gamma as a para. That type of substitution you may think. So just I have drawn that after electrophilic attack on the alpha position, on the beta position and the gamma position, how the sigma complex, because these all are sigma complex. So how the sigma complex are stabilized, because we know the rate of reaction of rate of aromatic electrophilic substitution is dependent on the stability. Means if the sigma complex is stabilized to a larger extent, the AES will happen easily. By the way, first of all, because of the presence of this electronegative nitrogen, reactivity decreases. This is the first point. Second point is we'll discuss how the alpha beta attack the positive charge delocalize. First of all, look at the canonical forms. In this case, alpha attack this canonical form, and in case of gamma attack, means alpha means ortho and gamma means paratype attack, this canonical form. Just look at these two canonical form where the positive charge goes on the electronegative atom, and because these two are less stabilized. Why? Because we know that nitrogen does not prefer to have positive charge. By the way, you may be little confused. You may ask that why, sir, we have previously seen that quaternary ammonium salt means R4N plus. This is R4N plus. This is all, in this case also nitrogen carries a positive charge, but this is a stable molecule. If this is stable, then why the nitrogen center is less stable? See, in this case the nitrogen is actually 8 electron species, means octet is filled, whereas if you look at this case, in this case the nitrogen is not octet filled, actually it is a 6 electron species like carbocation. Okay, how the 6 electrons? See, 2 bonds, 2 bond pair, and another case here the lone pair. So that's why this is less stable, whereas these quaternary ammonium salts are pretty stable. Okay, fine. Now, so this is the overall discussion. From this, what we have understood? We have understood in case of beta attack or meta-subatitution, the positive charge never comes on the nitrogen. Instead of that, it always goes over the carbon atom, which is relatively lesser electronegative than nitrogen. So this is more favored. By the way, the whole nucleus is deactivated. So in that context, this is relatively favored. Okay, so this is relatively favored than ortho and para. So don't think that it is activated at the meta position. No, it is completely deactivated, but compared to other positions like ortho and para, this is somehow more favored. Okay, fine. Now let's discuss the few examples. For example, aromatic electrophilic substitution on this simple pyridine nucleus. What happens if you take AlCl3 and Rx, means Friedel-Crafts, means Rx or RO6, Friedel-Crafts alkylation and acylation both. In this case, what you observe? No reaction. Why? Sorry. So previously I have told that nitrogen can form Lewis acid base adduct with this its lone pair, and actually that happens. See, at this aluminium pyridine complex. So in this case, this adduct formation deactivates. Why? Because some electron density further withdrawn from nitrogen to aluminium. So electron availability on this aromatic nucleus further reduces, and what we are doing actually, we are doing aromatic electrophilic substitution. So if the electron density reduce, how it will act as a nucleophile? Okay, that's why reaction doesn't happen. In case of sulfuric acid, reaction with sulfuric acid, just look at the temperature needed is 300 degree, pretty high, and the product yield meta-substitution is very low. Why? In this case, sulfuric acid act as an acid and pyridine act as a base and form this acid base adduct. Okay, so if this acid base adduct further deactivates for the reaction. Fine. Similar thing is observed in case of nitric acid, sulfuric acid. In this case, we know that nitronium ion is an electrophile which is generated, and check the reaction condition. See, it's a 300 degree centigrade 24 hours reaction, but still meta substitution, but 6%. Even if you do bromination at 300 degree centigrade, generally we don't observe halogenation at that much high temperature because it's too dangerous. And in this case, we get the meta product or meta dye substitution. By the way, one interesting point to be note that all the case this and this, they forms the meta substitution product. So in all case, meta substitution is favored. Okay, as I just discussed just before, but yield is less because of the electron deficiency. An interesting point is observed for halogen. Why? See, in this case, why we are getting dye substitution with a 26%. Okay, this is a significantly higher question. Why? You know that actually halogens, just remember, halogens are ortho and para orienting. This is a very important statement. Remember please, and deactivating. Okay, so why? Because the lone pair present on this halogen helps to do the reaction. And now a simple the topic I told that it's orthopara orienting, then you think that, sir, if it is orthopara orienting, then what we can expect that reaction could have been occurred orthopara with respect to bromine, means these three positions. Why it didn't happen? Because these positions are also orthopara to nitrogen, and the effect of nitrogen is more pronounced than the halogen. That's why the aromatic electrophilic substitution cannot occur on these three positions, whereas it occurs at this position. Okay, because another meta left, it's meta directing, so meta left. That's why the second meta substitution occurred at this position. Okay, fine. And by the way, if we want to use a selective nitration reagent like nitronium tetrafluoroborate, because we know that for nitration this is a actual electrophile and we have taken that thing, and in that case reaction doesn't happen. Why? Because of the formation of this Lewis acid base adduct, because in this case nitrogen, the lone pair of nitrogen is acting as a nucleophile to attack this nitronium cation. Okay, so that is the reason that reaction doesn't happen. Now from this we have understood it's a very big difficulty. This less reactivity is a difficulty because we need substituted pyridine derivatives. Means, what do I mean? That this is a pyridine. So if we need to do substitution using aromatic electrophilic substitution pathway, is there any possibility to enhance the reactivity? Obviously yes. Two ways are possible to functionalize this. And by the way, in this case, since we are discussing about aromatic electrophilic substitution, functionalization will happen this meta or gamma position, not these positions. Okay, there are some solution will come after some time. So how this could be done? Increase in electron density in the pyridine nucleus, because the biggest problem is the electron deficiency of the pyridine nucleus, and that could be counterbalanced by increasing the electron density in the ring. Having how? First of all, it could be plus I or plus R effect. Means this is, we may consider this thing as a electronic activation of pyridine. This is actually electronic activation of pyridine. Okay, now this at one point we'll discuss, and the second point could be increasing the bulkness of the ortho position or alpha position of the pyridine nucleus. Okay, such that protonation or Lewis acid based adduct formation could be prevented. Okay, so what we can consider this? We can consider this actually a steric protection. This is, we can consider steric protection to reduce deactivation. Okay, steric protection to reduce deactivation. If we consider in this way, then what happens? They can't coordinate with some proton or Lewis acid, so consequently the electron density on nitrogen will not decrease that extent, as I discussed. So now let's discuss this thing further. So let's discuss the point number 1, plus I effect. Okay, so increase in the example with higher activity with plus I effect. So how this thing happen? See, in this example we have taken methyl pyridine, and we know that methyl group has plus I effect. Okay, so it increases the electron density in the pyridine nucleus. Consequently, see, I agree this is a drastic condition, but still reaction occurs, and what we get, meta-substituted pyridine, but that meta is actually para to this methyl. What this substitution increases, that both factor, means meta with respect to this pyridine nitrogen and para with respect to this methyl, both are followed or maintained, and we got this product. Okay, now the second thing, instead of one methyl, if we increase the number of methyl into 2, then we can expect that reactivity will enhance further, because plus I effect increases more and more. Okay, and for that purpose, what they have taken, sulfuric acid and potassium nitrate mixture and 100 degrees centigrade. Just look at, in the previous case this is 180, right now this is 100. So the drasticity of the condition reduced somewhat. Secondly, previously we have taken oleum, which is very strong, and in this example we have taken concentrated sulfuric acid. By the way, how this reaction happens? First of all, sulfuric acid plus nitric acid. So this H2SO4 plus HNO3, they react, and ultimately what they, not HNO3, this is actually KNO3. We know that in this way what happened, first nitric acid is produced and potassium bisulfate is produced, and second step, sulfuric acid or oleum, this mixture act as a dehydrating agent, means water elimination, to produce the first of all protonation, second of all water removal, to produce the NO2 plus, which is the actual electrophile. By the way, one important information, please remember that sulfuric acid is stronger than nitric acid. Okay, and that's why it can produce nitric acid from its nitrate salt. Fine. So in situ actually we are generating the NO2 plus, which undergo reaction, and see, in this case also similar type of reactivity is observed. What do I mean? That the nitro group is first of all para with respect to this methyl and ortho with respect to this methyl. Okay, and it is meta with respect to the pyridine nitrogen. So all the conditions are counterbalanced. Now further activity increase means if we take the 1,3,5 trimethyl, so plus I effect will enhance further, and see, in this case concentrated nitric acid oleum at 100 degrees centigrade provides this product. Okay, and it is also ortho with respect to this 2-methyl group, and it is para with respect to this methyl group, and meta with respect to the nitrogen, pyridine nitrogen. By the way, another interesting point was, I told that during the nitration reactions, since very strong acid like sulfuric acid present in the medium, some acid based reaction possible. So that's why you can see that this adduct formation, but the deactivation induced by this protonation is counterbalanced by the plus I effect of this 3-methyl group. Consequently, the reactivity increases in overall perspective. Okay, but you may think a question that, sir, what are you telling? Is protonation? It is, you are telling. Is there any proof that such type of protonation occurs in the reaction medium? Directly it is difficult, but indirectly if we think, see, what do we mean by the protonation? Protonation means cationic nitrogen formation. So nitrogen in cationic nitrogen species formation. So if we take the prepared cationic nitrogen species, means this reagent. Okay, how this could be prepared? This could be prepared from this. This could be prepared from this 2,4,6 trimethyl pyridine plus methyl iodide. Why? Because the nitrogen has a lone pair, is in sp2 orbital, and it can act as a nucleophile, and methyl iodide is a very good reagent for methylation because this is a less bulky and iodine is a good leaving group. So through SN2 type process this reaction can happen and it will result pyridinium iodide. Okay, methyl substituted pyridinium iodide. So if the similar reaction condition is exerted, like concentrated nitric acid and oleum at 100 degrees centigrade, similar condition, this reaction occurs and gives similar product. So this thing proves this reaction follow this pathway. Okay, so this is the plus-I effect mediated activation we have discussed. Now let's discuss little bit about example through plus-R effect, means activation of increase of reactivity due to plus-R effect. And for this case, first example is I have chosen, that is NHCOCH3O3. We know that NHCOCH3 has a plus-R effect, but it is actually a weakly. So plus-R effect weak because the lone pair of nitrogen could be delocalized to the pyridine nucleus. This is point 2, and second, this is COCH3 part, that is also electron withdrawing. Okay, so both possible. Now, so what happens? We know that first of all, pyridine is meta-directing. So logically, based on pyridine, we can think that substitution can happen this and this. And meta with respect to pyridine is ortho. This is the ortho with respect to this nitrogen, and this is the para with respect to nitrogen. And we know that para substitution is more favored because in ortho position plus R effect works, along with that minus I effect works. But whereas in case of para position, the substituents only plus R effect works, no minus I effect, because it's a long distance, and minus I effect works through sigma bond. So effect is not that much pronounced. Consequently, what happened? In case of fuming nitric acid and concentrated sulfuric acid, what happens? It undergo nitration selective at this position, means, and yield is significantly improved, you may consider, which is 46%. Okay, because in case of pyridine, just remember the example. In case of pyridine, just it was only 6% yield, that is a very less, whereas in this case from 6% to we have achieved 46%. So next example, see in this case what is taken actually, that is 2,6-dichloroPyridine, and the simple reaction is done. See, nitronium tetrafluoroborate is taken, this is a selective nitration reagent, and just look at, it has taken acetonitrile and reflux. So we can expect acetonitrile reflux, means acetonitrile's boiling point, maybe I am not sure exactly, near about 80 degree you may consider. So near about 80-90, like that reaction temperature, the reaction is carried out. And for this such kind of reaction, 80 to 90 degree centigrade temperature means pretty low, because pyridine is a deactivated nucleus. And we know that halogen are orthopara orienting and deactivated. I have discussed few slides before. So what happens in this case? In this case, the chlorine's lone pair, you may consider it is orthopara orienting this. Okay, so since there are two chlorine, these two positions are equivalent, so as one position nitration occurred. Now if you want to get directly metachloro, which was our previous target, but previously we got simple 6% yield, that could be increased further. How? See, if we reduce this 2-chloro derivative, and that could be done in presence of copper benzoic acid at 180 degrees centigrade. Okay, by the way, one interesting thing, that why copper benzoic acid is selective although the temperature is higher, because copper is not that much strong alkali metal such that it can reduce not only the carbon chlorine bond along with this ring or this nitro group to something else. Okay, so that's why copper is chosen. And why this carbon chlorine bond is so active? Because you may consider this is a acid chloride type. Okay, this is a chlorine, so here means this is actually acid chloride, but if you compare this thing with, in this case, this is actually N, this, and this is, so actually this is not carboxylic acid, this is imine chloride. That's why this bond is pretty active and prone to cleavage because of the withdrawing effect of pyridine. Okay, so you may just look at, you may understand this thing little clearly by looking at this part. Fine, so that's why we get this thing. Now additional modification, better to say very good application of the chemical improvement is use of mercuric sulfate for this process. Why I am telling this? See, mercuric sulfate means it has mercury 2+. Okay, so mercury 2+ and pyridine we know that has lone pair. So what happens? This pyridine lone pair is donated to mercury 2+ and forms a coordinate complex, this thing, and because of this the activity improvised, And what do we think? Just some time before I told the pyridine and Lewis acid, in this case mercury, Lewis acid addact formation reduces the reactivity, because for Lewis acid based addact formation the electron density is drawn from this nitrogen to the mercury center. But in this case it's not exactly happening. Why? Because mercury has filled d orbital. So that's why what happens, that it can donate some electron density to nitrogen. And another thing, from periodic table, if we go from top to bottom, the electronegativity decreases, so it is more interested or capable to delocalize its pair of electrons to the pyridine nucleus. So consequently this chelation actually not deactivating, okay, it is somehow activating in nature. It's weakly activating. That's why the reaction occurs efficiently and ultimately result in pyridine 3 sulfonic acid. By the way, always remember that this mercury is not preferred in any reaction because of its toxicity. But why I have told this example to you? Because I know you should know the chemistry first. You should know the hazard first, of such that you can design something less toxic which is helpful for the mankind. Fine. And the last but the most important modification of pyridine for its activation through plus R effect is N-oxide formation. Okay, so in this case, see, this is pyridine N-oxide. How this is formed? The oxidation of pyridine with some oxidizing agent like hydrogen peroxide. And by the way, I have uploaded dedicated lectures on this pyridine N-oxides. I request you, please visit. Even I have uploaded MCQ. Please visit those videos and enrich yourself with the knowledge about this chemistry. Just as one example, I have included it here. So what happens in presence of bromine and thallium 3+? Actually, thallium is homologous of aluminium, means aluminium, gallium, indium and thallium. So it is actually a +3 and it is a 3+ oxidation state, and it is actually a Lewis acid here. And in this case, just look at this. The substitution occurs exactly the para position of the pyridine. So completely different pattern of reactivity could be achieved through this N-oxide formation. And you may think, sir, how this could be removed? This is the problem, nitrogen oxygen bond, and that could be removed by using reagents like zinc, means reducing agent like zinc, or triphenyl phosphine, because in case of zinc is oxidized to zinc 2+, and in case of triphenyl phosphate, what it is converted? This PH3 P double bond or triphenyl phosphine oxide. So in this way the oxygen is removed. So what we get ultimately? 4-bromopyridine derivative. Okay, so this is the overall discussion for activation of pyridine through plus R effect. Okay, so in conclusion, what you have learned today: aromatic electrophilic substitution on pyridine is difficult because it is less reactive due to the electron withdrawing effect of nitrogen atom, and pyridine is actually a meta-directing. Okay, it helps in meta-substitution, and its reactivity is similar like nitrobenzene actually, and that thing I have explained based on the canonical forms. An introduction of, based on the canonical forms, first point, and Lewis acid base addact formation, second point. Introduction of Lewis acid base or protonation. Introduction of electron donating group increases the reactivity on OES. We have discussed with plus I effect as well as plus R effect. And the most important achievement of today's discussion, N-oxide is very reactive, electron rich, because this is actually O- and N+, and if you look at one canonical form at least, that what happens? Oxygen pushes his electron and this goes here. So this is O, N double bond O, this is nitrogen plus, negative charge here. So in second canonical form, what can happen? That this can come here, it can come go. So this is N double bond O, this negative charge is here. So the nitrogen center will have the positive charge, so formal positive charge. So overall it increases the electron density in the ring, and actually this is ortho and this is this is para orienting. Okay, so this is the interesting part of this lecture. Okay, so I hope this video may be useful for you. So thank you all for watching this lecture. If you really like my teaching, please like the video and write your opinion in the comment box. And if you think this video is worthy, then share it with your friends so that they can also enjoy the benefit of my effort. And most importantly, subscribe my channel Chemistry the Mystery of Molecule, and please press the bell icon to get the notification of every single video I upload. So till now, stay happy, stay blessed. See you in my next video.